Hello class, let's take a look at a bolt design example. This is a very simple shear bolt design. All right, so I've summarized this problem up here on the board. We've got a 80 kilonewton force over here applied on this plate that's being transferred out to this side with two plates. This is actually not too dissimilar from the problem that we did in our previous section. I also labeled that this is going to be two bolts. You can't see it in this 2D drawing, but I wanted to make sure that we make sure that we divide that shear force divided by 2 when we do our design. We're given the failure strength of that bolt, average tau, and then we're also given a factor of safety of 2.5. That's actually pretty common for shear stress. We talked about how shear stress is not a great average shear stress is not an actual predictor, a great predictor of what the actual shear stress distribution is going to be. So we use a high factor of safety for that. For tension, right, we talked about sigma being a better estimator, so we're going to see smaller factors of safety there. We want to figure out what that diameter of our bolt's going to be, where we often use phi for that. So let's get started on this. I like to start these problems by first figuring out what our allowable average shear stress is going to look like. Remember, our factor of safety, we want to be greater than 1. That's always going to put our capacity in the top. So we say our capacity. In this particular case, we're going all the way to failure. And then we're going to say we want to put allowable down here. So to figure out allowable, we'll rearrange this, kick tau allowable. I'll go ahead and write that all the way out to allow. Tau allowable is going to be our failure stress divided by our factor of safety. That's what we expected. We always want that allowable stress to be smaller than our failure stress. Otherwise, we're going to be in trouble. Now, our failure stress is given over here. That's going to be 350 megapascals divided by our factor of safety, which is 2.5. If we do that division, 350 divided by 2.5 is going to give me a factor of safety of 140, or sorry, our allowable stress of 140 megapascals. So now we have allowable stress. We still need to figure out what our force is going to be in one of those bolts to relate stress to force and find our area. So step 2 is to find shear in a single bolt. I'm just going to call it V bolts. And looking at our object over here, we know that our failure point is going to be one of those connections between our plates, right? That interface between the top plate and the middle plate is where I'm going to pick, but if we pick the bottom interface, that would be the similar. So in that particular case, we know going across that interface is 40 kilonewtons. So to find V bolt, we're just going to take that 40 kilonewtons. That's what's happening at our interface. That's what's being transferred between this plate and this plate. And then we're going to divide by 2 because we have 2 bolts going there, right? 2 bolts in that profile, which means in one particular plate, we're going to see, or in one particular bolt, we're going to see 40 kilonewtons at that failure point. All right. So now we have our shear at one of those bolts, at one of the interfaces. So we can just rearrange this and say area is going to look like our force divided by our stress. In this particular case, let me get that correct. We want to use shear. And we want to divide that by our tau allowable. Now our shear in this particular case was 20 kilonewtons. Our tau allowable is 140 megapascals. Now I want to rearrange this a little bit. I'm going to say times 10 to the third kilopascals. Now at this point, you're probably looking at me and going, why bother with that? Why not just kick them both out and write them in terms of 10 to the third divided by 10 to the sixth pascals? You could do that. There's nothing wrong with that particular thing, but I like doing it this way because when I do this work, this is going to give me the kilonewtons and the kilopascals are going to cancel out, and I'm just going to be left with meters squared, which means when I get this small number here, because I'm doing 20 divided by 140 raised times 10 to the third, I'm going to get a very small number here. I'm going to get 0.000143 meters squared. I can get an area of that pretty quickly. The area for that particular plate is just going to be, or for that bolt is going to be 143 yeah, 143 millimeters squared. You'll notice that I moved that decimal 6 times, right? Because I'm going from meter squared to millimeter squared. So I've got to apply that, divide by 1,000, and also divide by 1,000 again. So that gives me 143 millimeters squared. Now, I'm very close to my answer. I have an area, but I was asked to find diameter, right? And this is where that case where we're going to go in and find our diameter using our area. We said area was pi times diameter squared over 4. So I can rearrange this very quickly and get diameter is the square root of area, 4 times area divided by pi, right? Rearranging this, kicking 4 over here and pi to the bottom. I get 4 times area divided by pi, which is going to look like the square root of 4 times 143 divided by pi. And I'm going to do that square root of 4 times 143 divided by pi. That's going to give me a value of 13.5 millimeters for my diameter. Now, the reality is you're probably not going to be able to define a 13.5 millimeter diameter. Let's go back and look at our answer, our question real fast. Now, in this particular question, if you look closely, it says to the nearest millimeter squared. Round to the 1 millimeter, right? Because you can't actually specify a 13.5 millimeter bolt. We're going to round up, right? When we're designing, we always want to round up. A bigger bolt is going to be safer. So we're going to round up here. And we're going to say a 14 millimeter bolt is what's required, right? A 14 millimeter bolt is what we're going to ask for in this case. We want a 14 millimeter bolt. We want to round up because a bigger bolt is going to be stronger and therefore more conservative or safer for this particular application.